thank you very much for coming. It's wonderful. There are so many people here. It's so many friends. It's great. So I want to talk about a project which I've been doing with Lassia and with many other people here over the past few years, about a project which, as we'll see, is, in a sense, trying to build a periodic table of shapes. And so I want to say first a little bit about the project, and about its history. I want to say a little bit about the key idea, which, as you'll see, doesn't really come from mathematics. It comes from string theory in theoretical physics. I want to say a little bit about the team of people who have made the project possible. And I want to finish off by saying a little bit about a kind of unexpected collaboration which came out of this, and with the artist Gemma Anderson, who's here, which has produced some unarguably beautiful things. So, yeah, let's say a little bit about the project itself. So, if we're talking about building a periodic table of shapes, maybe we should start by just sort of saying, what kind of shapes are we considering? You know, what sort of shapes are we thinking about? And so, mathematicians describe shapes using equations. And you can, so let me tell you, or let me remind you how this works. So if you have a point in the plane, you can describe it by two numbers, x and y. And what that means is, well, you know, you pick your favorite point, that one there, and then you draw two lines. And that black point being at x and y means it's x along and y up. And so now, how do I describe a shape using an equation? Well, every time I write down a formula with x's and y's in it, I can color all the points where that formula is true. And probably you remember from school or from your office just a moment ago that, you know, if you're thinking about the formula y equals x squared, then that's true on that parabolic curve there. So that parabola, that curve, is described by that equation. And similarly, if you have a different equation, say x squared plus y squared equals 1, well, that describes this circle in the plane. You know, this circle is the points where that formula holds true. So let's take away the axes and all the bump, because we've sort of got a sense of how this is working now. OK, so if you fiddle with the equation a bit, if you change it a bit, the shape changes a bit. You know, if I make it 2y squared rather than y squared, it sort of goes elliptical. If I make it 2x squared, then it goes elliptical the other way. Similarly, if I change that number right there to something bigger, the shape will get bigger. So we have this way of describing shapes by equations. There's nothing particularly special about the shapes being in 2 dimensions here. I mean, if I want to describe a point in 3-dimensional space, I can do it with 3 numbers, right? So for a point in 3-dimensional space, I can label with 3 numbers x, y, and z, which means, you know, you again choose your favorite point in space, that one. This time, draw 3 lines. And this black point being x, y, z means I'm x along and y along the other way, and then z up. And now, if I have an equation involving x's and y's and z's, then I can color all the points where that equation holds true. So, you know, if this is my equation, x squared plus y squared plus z squared is 1, then that describes a sphere sitting in 3-dimensional space. And if you have more complicated equations, you can describe more complicated surfaces. And we've understood for a long time that by manipulating the equations that define a shape, I can break the shape up, often into simpler pieces. And I'm not going to do that, because this is supposed to be, as Alessia said, 100% good. But let me just show you this in an example. So let's think about this shape. This is called a hyperboloid of one sheet. The equation's down here. This is a shape that you might well be familiar with if you've ever been up close to a cooling tower of a power station. They're this hyperboloid shape. And in fact, if you've ever walked up close to a cooling tower, they very often have straight lines scored in the concrete. So even though the shape itself is curved, on there you can find this family of straight lines. And in fact, the family of straight lines makes up the entire surface. So if you take a straight line and you spin it around in space at the same time as tilting it a little bit as you go, you sweep out this curved hyperboloid of one sheet. So from that point of view, this shape, this surface, this hyperboloid, you shouldn't think of as an atomic shape. You should think of it as kind of a molecule. And you should think of it as being woven out of those atomic pieces, which are the straight lines. So that's what I mean by finding atomic pieces of mathematical shape. So here, the atoms would be the lines from which that whole surface is woven. And the atomic pieces that we're considering are called Fano manifolds, after this gentleman, Gino Fano, who studied them pretty deeply in the 1930s. And yes, as I said, these are kind of atomic pieces from which more complicated shapes are made. I guess this insight that I can take shapes and break them up into basic pieces is only ever really going to be useful if I can tell you what the basic pieces are. And so let's just think for a minute. There's exactly one-dimensional Fano manifold. It's the line. We've seen that already. And that was known for a long time, actually known before Fano, so known to Felix Klein in the 19th century. And the basic building blocks, the basic surfaces, the Del Pezzo surfaces, there are 10 of these. And those were known, again, in the 19th century. So building the list of three-dimensional building blocks, finding the three-dimensional Fano manifolds, took nearly a century. So this was culminated in this remarkable work of Mori and Mukai in the 1990s, but building on Fano's earlier work in the 1930s and also work by someone who I didn't include a photo of, called Iskowski in the 1970s. And I guess what I want to talk about is much more recent work where we use a completely different set of ideas to approach this problem, a completely different way to find and classify these basic pieces. And this, I guess, was started in joint work with Alessio Corti, Sergei Galkin, Vasily Golishev, and Alexander Kapchek in 2013. And the thing that we've discovered is that it seems to be possible to find and to classify these basic pieces of shapes using a set of ideas from theoretical physics, from string theory, called mirror symmetry. And maybe one of the exciting things about this is there's absolutely no way that you're going to be able to get the methods that worked to find 1, 2, and 3-dimensional building blocks to work in general. they've gone as far as they can. Whereas these mirror symmetry-based methods should work in all dimensions. So this potentially opens the way to really understanding shapes in a new way. And so far we've been getting bits of this, quite a bit of this working. In particular, we've used these ideas to find new four-dimensional building blocks, both in joint work with Alexander Kapczyk and Thomas Prince, and also work by Ilana Kalashnikov. So we found many new basic four-dimensional manifolds, four-dimensional Fano manifolds, four-dimensional building blocks. Let me back up a little bit and tell you essentially what the key idea is. What are we doing? And as I said, the idea comes from string theory in theoretical physics. And string theory is one of the leading candidates for a theory of quantum gravity, so a theory that would include both quantum mechanics and general relativity at the same time. And I guess at its most basic level, the idea is that particles in the theory are not point-like, they're not tiny little points. They're tiny little vibrating loops called strings. These are really, really tiny, almost unimaginably tiny. So if you take an atom and you blow it up to the size of the solar system, you still can't see the strings. In fact, the strings are still smaller than an atom. So these are really small. Okay, and then different vibrations of the string give you the different particles that we see in sort of everyday existence. Something that's a bit strange about the theory, and that for a long time was thought of as an obstruction to it being a theory of real physics, is that in order to be a consistent theory at all, string theory needs there to be more than 4 space-time dimensions. So we experience 4 space-time dimensions, right? We can move around in 3 directions, at least if we jump, and we feel the flow of time. But depending on the flavor of the theory, string theory can't work as a theory unless space-time is maybe 10-dimensional, maybe 11-dimensional, maybe 26-dimensional. It depends on the flavor of the theory. And the way out of this conundrum that we don't experience these other dimensions, where are they, is that perhaps they're what mathematicians would call compact. They're curled up extremely small. So somehow you should think of ordinary 4-dimensional space, 3 space dimensions, 1 time dimension, as being big, and then stuck to every point of that space-time is some really small, kind of size of a string, small, curled up extra 6 or 7 dimensions. So pictorially, that's how we approach this problem. We think about a model of physics where you've got your ordinary space and time, and you've got your favorite shape, that one, stuck to every point of 4-dimensional space. And that's what you imagine space-time to be. And I guess from a bird's eye view, what we're going to do is we're going to think about what physics would be like in such a universe. And it turns out that you can tell the difference between that shape, that one, the curled up one, being an atom, or that shape, the curled up one, being a molecule, being something that you can break up, by looking at properties of what physics would be like in this universe. So we know that it's certain that our own universe is not like this, does not have a Fano manifold curled up as its extra dimensions. The physics certainly isn't realistic. One way you can tell that is, do you remember we discussed that sort of different particles were different vibrations of the string? And so even though we don't experience these sort of extra dimensions, the possible vibrations of the string really do feel that. So you can see bits. So exactly what that shape is affects what particles come out in the theory. And the ones that we're thinking about don't have any massless particles. So given that you can see me, it's not realistic. But nonetheless, we can take this strange model where we've taken our favorite shape and stuck it to every point of space-time and thought about what the world would be like. And we can try to analyze this using techniques that physicists use to solve realistic models. In particular, there's this extremely powerful tool called mirror symmetry, which says, well, instead of thinking about space-time like that, this is what's called type 2a string. You can think about, you can model the system equivalently in a different way called type 2b string theory. And what comes out of that is that thinking about our shapes and our Fano manifolds and whether we can break them into pieces, when you take it across mirror symmetry, what you find is that everything is encoded in, the world is described by what's called a Landau-Ginzburg model. And that's a very visual thing. So a Landau-Ginzburg model is basically a shape divided up into slices. So it's, if you like, it's a space, a shape, but it's got a function on it. So every point of this space knows its height, let's say. So I'm graphing the function this way, up and down. So the shape that I'm thinking about, the Landau-Ginzburg model, comes divided into slices by the energy function. Smile if you're with me. So we end up thinking about these spaces divided into slices. And so then there's a question, right? So I'm trying to find these basic pieces, these atomic pieces of shapes. And I'm going to run this through mirror symmetry, and I get one of these Landau-Ginzburg models, one of these sliced up shapes out here. And the thing is, Fano manifolds, the things that we're looking for, these atomic pieces, are very special. So when I run it through mirror symmetry, I should get very special ones of these guys out. So let me tell you what very special means. And what it means is, how do you tell? Well, it's to do with what are called critical levels. So the level is a slice. What's a critical level? Maxima are critical levels. So things that look like mountain tops. And minima are also critical levels. I can't show this on the picture because it's underneath, but there's one sort of there at the bottom, right? So there's two critical levels here at the top, one at the bottom. And there's another sort of critical level, which is where the slice is not smooth. Let me tell you what I mean. So you know this shape has come divided up into slices. What does it mean for this slice not to be smooth? Do you mind if we look at a slice really high up at the top, near those mountain top peaks? did you see? So can you see the slice is like 2 circles? If I move it down a bit, it's still 2 circles, but they've got a bit bigger. Both of those are smooth. They're sort of smooth curves. If I push it down a bit further, can you see it's become one smooth curve? When you sliced beneath the mountain pass there, look, there's a sort of smooth curve all the way around. That's the level. So, somewhere as you were sliding your surface down, you started off as 2 circles. In the end, it's come out as 1 circle. Something happened in the middle. That happened. Can I tip it over so you can see? Do you see? Just as the 2 circles touched each other, it picked up a kind of cross in the middle. So that slice is not smooth because it's got that X in the middle of it. Okay, so these are critical levels. They come either from the maxima, or from the minima, which I forgot to show, or from these kind of non-smooth slices. Do you see the non-smooth slice happens at the pass between 2 mountains? Do you see what I mean? Like, this is like a mountain pass. You can go up over there, but there are 2 peaks to either side of you. Okay, so if you taught or experienced multivariable calculus, and these are called saddle points for mountain passes, will do. Okay, so why am I telling you this? I'm telling you this because I'm trying to find basic pieces of shapes of these Fano manifolds. And we've run them through mirror symmetry, and we've got this sliced up shape, this Landau-Ginzburg model, out. And I'm trying to tell you what corresponds to being Fano, what sort of very special it means. And what it means is Fano manifolds turn out to correspond to Landau-Ginzburg models with really, really few critical levels. In particular, this one right here definitely is not the mirror to a Fano manifold, because I'm going to show you that it's got some kind of extra or redundant or unnecessary critical levels. So do you remember we had those 2 maxima? We have the 2 maxima and that slice which is not smooth, and we've got the one at the bottom. Can you imagine kind of like taking those mountains, just changing the height of everything to make those mountains lower? Actually, we've still got the same number of critical levels. We've still got 2 maxima, and we've still got this saddle, this mountain pass, and we've got the one at the bottom. But if I keep going, if I keep pushing this down, look, I cancelled off 2 maxima and a saddle. So this now only has 2 critical levels, the one at the top and the one at the bottom, and the other ones have disappeared. So that one that we started with couldn't be mirror to a Fano manifold because it has sort of unnecessary critical levels. Can I do another example? So suppose you found yourself a Landau-Ginzburg model, a sliced up shape like this. I claim that that definitely doesn't correspond to a Fano manifold because it's got huge numbers of mountain tops and huge numbers of valleys and mountain passes that I didn't really need. Can I make all my mountains a bit smaller? See, it's sort of flattening out, and all of the peaks are going away, and all the valleys are going away. I've got to that, where everything is kind of smooth now. How many critical levels does that have? 4. Why? So where are they? Yeah, so there's one at the top for sure, because there's a maximum. There's one at the bottom for sure, because there's a minimum. If you imagine just being very small and climbing up here, this would feel like a mountain pass. Because look, you'd be going over there, and you'd have stuff going up above you on both sides. So there's also, sorry, that's maybe a better picture. Look, there's 4. One from that mountain pass, one from that upside down mountain pass, that and that. So the thing we first started with definitely wasn't the mirror partner of a Fano manifold, because it had all of these unnecessary mountains. And so we've gotten ourselves down to 4 critical levels. Let's try and do better. So let me try just wobbling this a bit. If I just tip it over. It's still got 4. But if I keep going, if I have it just horizontally, somehow, magically, instead of having 4 slices like that, I now only have a top slice and a bottom slice, the maxima and the minima. And all of the rest of them are not critical. So I guess what I wanted, so what was all that about? Okay, so we're looking for these atomic pieces of shapes, and we've applied this idea of mirror symmetry, and we've come out and got this Landau-Ginzburg model, this sliced up shape. And we said, I really don't want very many critical levels, very many non-smooth slices. And that really constrains both the shape itself. Do you remember when we sort of flattened all the mountains and raised all the valleys? And it also constrains the way it was sliced up, where we sort of pushed it over to make them least possible. So it's a kind of very rigid thing. It's a very special thing. Some of you are possibly feeling grumpy at this point because if I'm thinking about smooth manifolds, I can always get down to 2 critical levels, so I must be not telling you something. The thing I'm not telling you is don't use smooth manifolds. Use don't use smooth functions. Use algebraic functions or holomorphic functions, and then look for minimum numbers of critical levels. Okay, so that's sort of the idea, is that we're looking for these basic pieces, and we use these ideas from physics to turn it into a problem about finding these very special Landau-Ginzburg models, these very special sliced up shapes. And in fact, we have a more precise conjecture, not just that what I get turns out to be one of these things, which is called extremal, where you have as few critical levels as possible, but actually I believe that we can tell you exactly what the mirror partners to Fano manifolds are, what you get on the other side of mirror symmetry. This is this idea of, they're called rigid maximally mutable Laurent polynomials, invented by Alexander Kapchuk and Katal Tveitan. So we believe that we can find that when we run it through mirror symmetry, we know exactly what the basic pieces look like. So what have we done so far? Do you remember that we already knew that there was one Fano manifold in dimension 1 and 10 in dimension 2 and 105 in dimension 3? Okay, so in dimensions 1, 2, and 3, this is true. I can prove this. We can prove this. This is work with Alessio Corti, Sergei Garkin, and Alexander Kapchuk. But as I said, the quite exciting thing is that this isn't limited to any particular dimension. So we've started to explore in dimension 4, and using these ideas, we found many new 4-dimensional atomic pieces. So 528 in joint work with Al Kapchuk and Thomas Prince, and Lana Kalashnikov has found a further 138. So these ideas are already kind of shedding light where there was no light before. I should say this really isn't my work. So I've been very lucky to have sort of large ongoing collaborations with Alexander Giventhal, my thesis advisor from Berkeley, with Alessio, who you have met here, with Hiroshi Iritani, who unfortunately isn't here, he's in Kyoto, and with Alexander Kapchik, who is now, he might actually be here, but in any case, he's at Nottingham. And there's this great team of people, colleagues and postdocs and students at Imperial, who, we've worked on this together. I mean, both on the sort of mirror symmetry theory package, which underlies a lot of this, and more recently on the Fano project itself. So this kind of this team, working with all these people has really been totally essential to the project, because, I mean, I haven't said enough for you to necessarily be able to see this, but this kind of this touches many different areas of mathematics. So geometry and computing, and touches theoretical physics, touches number theory. And so, these people have really brought essential expertise and ideas and to the program, without which it just wouldn't have worked. I want to say a slightly grumpy thing, given what's happening at the moment. It's in a sort of post-Brexit environment. So I just wanted to say something I'm kind of worried about. Because just sort of thinking about people I've worked with, my team, this project, right? Let's just imagine what would happen if people couldn't move about from country to country. So, Alessio is Italian. Hiroshi's Japanese. Andrea Brini is Italian. Amin Golanpour is Iranian Canadian. Yunfeng Jiang is Chinese Canadian. Paul Johnson is American. Christina Manolaki is from Romania. We don't actually lose everybody. So Al Kapchik is British, so is Andrew Strangeway.
From a Polish family.
Sure, yes. Mohammed Akhtar is also British, Thomas Prince. Andrea Petracci is Italian. But obviously that's not working. Sorry? There we are. You can blur yourself, I guess. Alana Kalashnikov is Canadian. Navid Navaju and Alex Kite, both British. Sara Filippini is Italian. General da Silva Jr. is Brazilian. Liana Heuberger is Romanian. I mean, so there's sort of been lots of nonsense talked around Brexit in various ways, but I'm just a bit worried, because it's not. I'm just very specifically worried about this. It's not possible to do science like this that crosses so many disciplines without people being able to move around, without people being able to take ideas from one country, one university, one place to another. There isn't, I think. There's not. This expertise certainly doesn't exist in one university. I don't think it even exists in one country. It certainly doesn't exist in our country alone. So, anyway, I'll stop being grumpy now. I can unblur everybody. I guess I wanted to finish by discussing another aspect of the project. Should really stay closer, shouldn't I? Another part of the project, another collaboration with the artist Gemma Anderson. So you may have already seen as you came in some of the work that's come out of this. In any case, please take a look during the reception afterwards. But this collaboration started, this was complete serendipity. So Anderson happened to be in Imperial, visiting the materials science department. At the time that the Imperial College magazine had lots of pictures on the front of it from our research project. And so Anderson has a kind of long-standing interest in sort of geometry and form as the basis of classification, sort of using drawing and form to understand the world and to classify the world. So it's not the same, because I guess at that point Gemma was mainly thinking about actual physical things. I mean, she was drawing actual physical minerals in the actual physical materials science department, right? So, but this has become a kind of very surprising and enjoyable collaboration. So, I mean, to begin with, Anderson's made many drawings and etchings of the geometries that we've been thinking about and studying, sort of giving them really physical form. And we've also made some things together, both sort of investment casts of some of the Fano geometries, and then also going back to a really old-fashioned way, really traditional way for geometers to understand complicated shapes. So, you know, if you go back to the 1890s, these people who were studying the geometry of surfaces, they made these beautiful slice forms, kind of, they made the surfaces that they were considering so that they could visualize them. And so we've been doing something similar here. The slice form is kind of etched with forms both from the natural world and from different sort of geometrical forms that are sort of reminiscent of the space that's being portrayed. So we've been building slice forms and investment casts as well. It's been, and actually, it's been sort of eye-opening in as much as it's surprising how close our creative processes are in terms of drawing as a way of understanding something, sort of drawing and visualization as the kind of root of this understanding. If you come into my office, or if you come into Alessio's office, then you'll find a lot of scribbled drawings on the board where we're trying to actually visualize and understand and focus in on parts of the spaces we're thinking about. And similarly, Anderson's process around drawing from life and kind of very careful observational drawing and form-based classification. Anyway, it's been enormously enjoyable and produced some really, as you'll see, quite beautiful things. Yeah, I mean, the whole thing's been quite enjoyable, really. It's a little bit difficult to believe I'm actually getting paid for this. So thank you very much.
Does anybody have a question for Tom? Unfortunately, you may have to shout it. I don't know that we have any technology.
It's not mandatory to have questions, but I would be very happy to answer them if you
Well, don't be shy. Yeah.
You mentioned that these three-dimensional manifolds are atomic.
Aha.
It's elemental. What interesting things can you build by combining them?
So, I mean, there's this sort of general idea that this is called the minimal model program, that geometries fall into three sorts of basic pieces, kind of positively curved basic pieces, flat bits, and negatively curved basic pieces. So, what the minimal model program tells you, roughly speaking, is that you can weave any space out of those pieces. So I guess the analogy of molecules is not right in one way, in the sense that you're not kind of like plugging the shapes into each other. You saw how we were weaving the surface out of those pieces. So if you use weaving as your operation, then you can express any shape as a combination of woven together from these flat bits, positively curved bits, and negatively curved bits. So now, why am I only looking at the positively curved bits? Well, it turns out maybe our best way of getting at the flat bits is also just by thinking about finding Fano manifolds and then slicing them up. So we hope to get as a sort of a fairly broad collection of basic objects that you can then weave almost anything out of.
Yeah. You got another question.
Do the atomic pieces only exist in Euclidean space, or are there hyperbolic atoms?
So, right. So that's a good question. So the answer is, the actual answer is we don't know. But what we've found so far is that you can realize all of these shapes by cutting them out of using equations from some fairly simple from fairly simple ambient spaces. So not quite Euclidean space, but these things called toric varieties and these things called quiver flag manifolds. So like a fairly small collection of ambient spaces that we understand, and you can find everything inside those, cutting them out of using equations. In terms of the sort of hyperbolic-like pieces, those are the sort of negatively curved things that I don't know how to get at this point. So there will be sort of negatively curved pieces, but at this point I can't say anything about them.
What were things?
I think on one of your slides I said that there was 527 plus 1 toric varieties. What's the plus 1?
I love you. This is such a... Okay. So all right. So let's see. Okay. So what we've done to date, this bit, we already knew the classification, right? We already knew what the pieces were, and now I just tell you how to find them in some better way. And it is better, and it's kind of reassuring, okay? And these guys, the 527 and the 138, so Al and Thomas and I and Ilana went looking systematically for these shapes, and we found the shapes first, and then we ran them through the program and we found the Landau-Ginzburg models. That's fine, but that's not how this is supposed to work. Remember, you're supposed to start on this side where everything is easy, and then run it backwards to find your unknown shapes. That's what the one was. So that's the kind of proof of concept, that you find its mirror pair first, and then you find the shape that you didn't know was there by looking at its mirror shadow.
I don't know how this is, but on the toroid example, you had a horizontal toroid, and you'd set the maximum and minima in the x direction.
Uh-huh.
Now, if you're working in 4D,
You know, you should shout your voice.
It's okay. I'll repeat. Don't worry. I'll repeat it.
if you're working in 4D, how can you have it as a function of all 3 dimensions or just 1 dimension to base that minimises the layer connecting?
So the question was, so in my example here, where I had this one, I kind of had height going this way, and somehow I had sort of x and y going this way, and then how, the question was, when I'm thinking about higher dimensional spaces, how will I be able to minimize, so if I'm thinking about a 4-dimensional thing, how will I be able to sort of find the minima, sort of visualize the minima in that situation? Was that?
That ends with the reorientate.
Oh, I see. How would I imagine
Well, you had the maximum minimum as a function of x, as a function of the height when you put it
Yes.
horizontally.
And then how do I do it? Okay, so here, right, so I had the maximum minimum as a function of height. So now what do I do when I suddenly have more dimensions? So I mentally put myself in one extra dimension. So your x, y, and z and w will be some four-dimensional piece here, and then height, the value of the function. I just make a new dimension, and I make my slices that way. And so I can still do this. It just becomes harder to visualize. Maybe, yes.
Has it been proved that the number of Fano manifolds of a particular number of dimensions is finite?
That's a really good question. I should have said that. Yes, it is known that in each dimension there are finitely many Fano manifolds up to deformation. So, up to squishing. It turns out that's very non-constructive in as much as the bounds that come out of that are like 10 squillion. And we know, before, in 4 dimensions, so at the beginning of this, we kind of knew around 200, maybe 300. Now we know 700. The theoretical bound is it's got lots and lots and lots of zeros.
Could you talk about some applications of this research, or what is to be
So why should one care? I think that's a very good question. The most likely direct application is something that you can't really see here from what I said, is so we believe that we know the mirror partners to Fano manifolds, these kind of rigid, maximally immutable Laurent polynomials. So then I want to go and find those guys. And that's a computer algebra problem. That's a problem that is amenable to computer algebra. But it's a very challenging computer algebra problem. So in order to guide all of this work, essentially to do the mathematical experiments that underlie this, we've built a lot of infrastructure for taking computational algebra questions, distributing them across hundreds and thousands of machines, reaping the answers. So the actual most direct thing is likely to come from the tools we build to solve the problem. So you could think of this as the Google plan, where you get to work 20% of your time on something that really motivates you, but the wrong way round. It turns out, though, that there are quite surprising connections with various other areas of mathematics. So, for instance, I don't know why this is true, but you can build codes starting from Fano manifolds over finite fields. So, somebody texted me from sitting in a number theory lecture saying, somebody's just referenced your paper in a number theory lecture. It's often hard to predict where the connections will be, but there are certainly interesting connections to number theory and to physics and so forth. But probably it's going to be the computer.
Does this relationship between the Fano manifolds and the Landau-Ginzburg model, does the fact that you've used mathematics, or you've used a concept from string theory to relate those two things, does that get us any closer to validating string theory as a whole?
So the question was, given that these ideas that are essential here come from string theory, does this get you any closer to validating string theory? Is this a mathematical experiment to test string theory? So, yes, in a sense, but okay, let me be skeptical about that. So what I'm testing here by doing this is the internal consistency of string theory, right? So that's not really a test that it's a theory of everything. But it's probably a test that it's a theory of something. Right, so because the coincidences are too good to be true. This feels like a kind of this feels like strong evidence for these body of techniques all coming together and being a coherent model of something. a long time ago, string theory was a theory of the strong nuclear force, until people realized it wasn't very good as a theory of the strong nuclear force, right? So, maybe it will be a theory of quantum gravity, maybe it'll be a theory of low temperature superconductivity or something, but it's all we're testing is internal consistency. Let's go to the reception.
There's probably some booze out there.
It's downstairs, I think. Yeah. Follow us here.